He earned his PhD at some other school in California, not called Stanford. I think Berkeley, that was it. He was at Berkeley. His work on super collider physics and the Higgs boson has been recognized with one of the highest prizes from the American Physical Society, the Sackharov Prize. But I would say what sets him apart from most of his colleagues is not his intellectual prowess, but more importantly his ability to communicate his passion and his sincere belief that science and physics and particle physics can help reveal the deepest secrets of our universe. So without further ado, let me introduce Dr. Christopher Quigg. Thank you. Sir.
Thank you. Thank you for coming tonight. It's a great pleasure to be with this audience. You know, all of us think of ourselves as explorers, and explorers need support, of course, financial support, but even more important, being able to come home from our voyages and share our discoveries with people. And we've had the pleasure over many years of doing that with this audience in the Fermilab community. So I thank you for being part of that. It makes our work meaningful. So 50 years ago, this 6,800 site on which we find 6,800 acre site on which we find ourselves looked like this. There were the 400 residents of the planned community of Weston on the east side of the laboratory. Many farm families who had settled here and tilled the soil, the Illinois soil, for many years. And it's very different now. In the space of a few short years, it became an international destination for physicists, welcoming scientists from all over the world and producing results that are valued by people all over the world. It's also named, as you've just heard, for Enrico Fermi, the Italian-American physicist, who was revered by all of us. He died in 1954, so he never got to see Fermilab, nor did we benefit directly from his input. But he was someone that we called the last universal physicist. He was a master of both theoretical physics and experimental physics. And this is something he knew all the subjects of physics and was able to communicate and teach them. So he's been one of my personal heroes, and it is wonderful for me, and I think for my colleagues, to be at a laboratory that bears his name. The founders of our laboratory, Bob Wilson and others, wanted this to be a quintessentially American laboratory, but open to the world at large. And one of their first acts was to honor the legacy of what had been here before. So you see on the east side of the laboratory in circle, sock circle, a number of the original farmhouses. Several of them are gathered together here in the building that we call Aspen East, which has served as a dormitory for many years. The little houses in the village of Weston have been used as dormitories or residences for visiting scientists, originally for labs and office space in the early days. And the roads in the east side of the laboratory in the Fermilab village have been named for some of the Native American tribes who were inhabitants of this area even before the Europeans came. Our founders made no little plans. This is an early scheme in which you see the village on the right, the big ring there, which is nearly 4 miles around, 2 pi kilometers around, was the sketch of the accelerator. And over time, this plan has evolved and been put into shape. And this is the conception of the laboratory now. You see that it bears the same outlines as the original, but with a number of very important additions that point to our present and our future. Now, Fermilab was founded at a time when the national instinct to get together and to do complicated, difficult, expensive things for the common good was much in evidence. So that was good. It was also a time of social upheaval. It was a time in which the nation was coming to terms with its legacy of segregation in the past. And the funding of the laboratory was threatened by the fact that the state of Illinois and the surrounding communities had not yet adopted open housing legislation. Our founders, Bob Wilson and Ned Goldwasser, his deputy, both by that exigency but also by personal conviction, wrote this statement of human rights for Fermilab. It says in part, it will be the policy of the National Accelerator Laboratory to seek the achievement of its scientific goals within a framework of equal opportunity, employment opportunity, and of a deep dedication to the fundamental tenets of human rights and dignity. And then skipping over here, in any conflict between technical expediency and human rights, we shall stand firmly on the side of human rights. So that's been a beacon to us for all of this time. They didn't just talk or write, they also put their ideas into action. And one of the first actions was to find a group of young men in Chicago who had demonstrated a technical aptitude to bring them to the laboratory and begin training them to be technicians, eventually engineers, and so on. Part of their training took place at the Oak Ridge National Laboratory in Tennessee. And here they are on the tarmac, I guess it must be at Midway Airport, about to board their flight to Oak Ridge for the beginning of their training. Many of these people have been with us for decades, and all of them are among the builders of the laboratory. Wilson was a man who was born in a place that he called Frontier, Wyoming. No one knows whether it actually exists or not. And he wanted, again, this to be an American laboratory, so he imported 5 bison, to which the state of Illinois added a few other very early on. And as often happens when you try to do something interesting and good, it has unintended consequences. So the urban or maybe suburban legend grew up that the buffalo were actually here as canaries in a mine. There was no internet in those days, but had there been an internet, you would have read there that they're very sensitive to radiation, and when they detect radiation, their hair falls out. If you come back in the late spring, when they're shedding their winter coats, you will find that all of their hair falls out. So don't be frightened by that, and come and enjoy our buffalo. So here was the groundbreaking for the main ring, our 2 pi kilometer round ring. You see everybody was there. Everybody's wearing hard hats except the boss. Everybody has a big clunky shovel instead of the boss. The boss has a gold-plated or maybe brass-plated shovel. If you'd like afterwards to come up and take a selfie with Wilson's shovel, please feel free. Don't harm anybody around you. And my chief operating officer will be happy if you wear a hard hat while doing that. So there it was. That was the beginning. I came here as a visitor. I was a fresh PhD, and I came here for a week in the spring of 1971. And I remember 2 things. One is that there was a lot of mud, and the second that it seemed like a very exciting place. So now we look at the chain of accelerators. The first big piece of the accelerator was a reincarnation of one of the earliest accelerators. It's called a Cockcroft-Walton machine. This was the machine in England that was actually first used to artificially disintegrate the nucleus, and it still, until recently, served as the first stage of the accelerator at Fermilab. It's a very efficient way of getting up to a few tens of thousands of volts. Next comes the linear accelerator. There it is. He's actually cleaning, not sleeping. It's called a linear accelerator because it's in a straight line. That's the second stage of the acceleration. Then comes the booster accelerator, which is just behind us out back, which takes the protons up to about 8 billion electron volts. Here's some components of that being installed. You see lots of people doing lots of hard work in those days, and you saw some mud. Here's the main ring tunnel being finished. Again, lots of mud. This was done by cutting the ground away, so digging the ground away, installing a concrete flooring, and then using hoops to cover it, and then covering that back up. And here's what the main ring looked inside. The reason for this plastic is that, as with many Bob Wilson constructions, the roof leaked, and so the magnets, which have plenty of problems on their own because they were really working to a tight budget and being exceptionally frugal, the magnets got wet and waterlogged and things like that. So the year before they got the machine to work, I was not a member of the Fermilab staff, but I'm told that it was the longest year in the life of many people who were doing that. But there was an end, and on February 12th, early in the morning, in 1972, they managed to accelerate the beam of protons up to just over 100 billion electron volts. The previous world record was held by a machine in Prodvino in the Soviet Union, which was 76 billion electron volts. So it was great celebration for having seized the world record. And in a nice touch, some of our colleagues from the Soviet Union contributed a bottle of vodka extra, which was drunk in the control room on the occasion of this. In the morning, the first experimental events were recorded. And this is a very interesting collaboration. This was in 1972. Richard Nixon and Leonid Brezhnev were the leaders of the two superpowers. They were both pretty tough characters. Nevertheless, they thought that it would be nice to encourage cooperation between the two superpowers, rival superpowers, in an area which could be of no threat to anybody, namely particle physics. So that was our good fortune. And through the friendships of some of our colleagues on this side and on the other side, one of the first collaborations formed was this one from the Soviet Union, the Joint Institute for Nuclear Research in Dubna, and from a number of American institutions, including Fermilab. They had the clever idea that, it was one thing to accelerate the protons to high energy. It would be another trick to actually get them out of the machine so you could do experiments. So they resorted to an old technique, which was intercepting the beam as it was circulating in the ring. And they did this with a thing that was a little motor that could turn at 3,600 revolutions per minute. On this was a polyethylene foil, specially shaped, and so it went around and around like that. It would intercept the beam, and they could detect particles that were scattered by this very thin target, so thin that it wouldn't intercept, wouldn't bother too much, wouldn't absorb too many of the beam particles. And so they took their first data that very first night that the accelerator reached 100 GeV. I've now seen a photo of the prototype of their little apparatus, and I did a little research, discovered that the prototype was made in 1970. In 1971, someone else invented the weed whacker, and if they'd been a little faster to bring their invention to market, we could have paid for the rest of the experimental program. But they were focused on the physics. Later on, they added a new feature, which was to send a supersonic jet of hydrogen gas through the beam. That was even better, even more tenuous beam. And because they were inside the accelerator, they could actually make measurements as the beam energy increased during the acceleration process. So that was a very nice piece of work, and it was wonderful on the day the accelerator began to work to get some data. Within a couple of weeks, by the beginning of March, thanks to twiddling with some dials in the radio frequency building, the design energy of 200 GeV was reached, and that was cause for a celebration, not with vodka, but with some unknown liquid this time, for the days of Dixie cups. Now, the first experiment to actually publish data came from this device called a bubble chamber. So this was a 30-inch in diameter device, under pressure, superheated liquid hydrogen, so that when charged particles fly through it and relieve the pressure, a chain of bubbles forms. They look like this. This was brought to us by people from Argonne National Laboratory, and I don't know if this is an early example of product placement or what in the right corner there. So bubble chamber pictures are iconic and wonderful because they give you, when you take stereo views, three-dimensional views of the particles. It's a little clunky in the sense that it's slow, and you see a picture is there forever, but then you digitize the picture so it's real physics to analog to digital and back and forth. But they are beautiful and they're iconic. And we were also taken by these when they first came because it was the first step into a new energy regime that we just wanted to collect these pictures. I remember Richard Feynman coming here and wanting to take home the sheaf full of bubble chamber pictures because it was our first look at many particles, many was 10 in those days, being produced. Here's another one of those images. So they actually produced the first publication. Here's a scanning table showing one of our scanners looking at the bubble chamber pictures. They would be projected on a very flat table, and then either using curved pieces of plastic or later on by being able to digitize them with electronic devices, one could measure the trajectories of the particles coming out. So they submitted on the 21st of July, and this was published in the Journal Physical Review Letters, the first experimental publication from Fermilab. What they did here was a stupendously simple thing. They simply counted the